Now let me define the definition of cancellation law in a ring R equipped with binary operation plus and dot. By definition of a ring, we know that R under plus should be an abelian group, and in this case, since R under plus is an abelian group, so it will always satisfy the cancellation law under the binary operation plus. But now for a ring to satisfy the cancellation law, it must satisfy under multiplication, it must satisfy this condition that whenever A, B, C belong to R with A not equal to 0 and AB is equal to AC, then it must imply that B is equal to C. That means A has been cancelled from the left side, and this is called as a left cancellation law. And whenever BA is equal to CA, it implies that B is equal to C, then this will imply that it satisfies the right cancellation law. So a ring R will satisfy the two cancellation laws, that is both left and right, under multiplication. Note down this thing, it should be under multiplication. If whenever AB is equal to AC, it must imply that B should be equal to C with A not equal to 0, or BA is equal to CA, it will imply that B is equal to C. Now, not all the ring will satisfy this cancellation law. So let us keep the condition under which the ring will satisfy the cancellation law. So before that, let me just recall this definition of divisors of 0. Let R under plus and dot be a ring if there exists an element A and B belong to R such that the product AB is equal to 0 or BA is equal to 0, but neither A is equal to 0 nor B is equal to 0. Then in this case, element A and element B are called the divisors of 0 or the 0 divisors of R. Why? Because neither A nor B are equal to 0, but their product is equal to 0. So in this case, A and B are called the divisors of 0. Now let me define this next definition of this theorem. And in a ring R, the two cancellation law holds in cancellation laws hold in if and only if R is a ring without 0 divisor. That means if a ring R has no divisors of 0, then in that case it will satisfy the two cancellation laws. So now let us prove this once it is if and only. Suppose we assume first this one. Let us assume that R is a ring without divisors of 0. That is, whenever the product AB is equal to 0, then at least one of the element A should be equal to 0 or B is equal to 0. So let us take here three elements A, B, C belong to R, satisfying the condition that such that AB is equal to AC with A not equal to 0. What I need to show that this ring satisfies the cancellation laws, that is both left and right, if it is a ring without 0 divisor. Now AB is equal to AC with A different from 0. So now here AB, transfer this AC to this side, you will get AB minus AC is equal to 0. Now A is a common factor from here, so it will be A into B minus C is equal to 0. Now since it is a ring without 0 divisor with A not equal to 0, so the only possibility for us from here is that B minus C should be equal to 0. Transfer back this C to that side, then you'll get B is equal to C. So what we have now is that AB is equal to AC implies that B is equal to C if it is a ring without 0 divisor. So this implies that left cancellation law holds. Similarly, in the same way, you can show the right cancellation law by taking, suppose BA is equal to this one, CA. So in the same way, transfer this one to this side, then you'll get BA minus CA is equal to 0. And this implies that B minus C into A is equal to 0. Since A is not equal to 0 and since R is a ring, this is important. This is our assumption that R is a ring without divisors of 0. So it must imply that this second element B minus C should be 0. And again from here you'll get B is equal to C. That means the right cancellation law holds in this case. Whenever BA is equal to CA, we have B is equal to C if R is a ring without 0 divisors. Now the converse part, let us consider, suppose the two cancellation law holds. Suppose the two cancellation law holds. Now what we need to prove is that this ring has no divisors of 0. Now so let us take element A and B belongs to R, with A different from 0, but their product AB is equal to 0. So how to prove that B should be equal to 0 in order that R is a ring without 0 divisors? So what you need to do now is, now AB is equal to 0. AB is equal to 0 will implies that AB can be written as A into 0, because A into 0 is always equal to 0 in a ring. So now here you see that since by the assumption that the two cancellation law holds in R, so which means that the left cancellation law holds. So this implies that AB equal to A into 0 means that B should be equal to 0. Similarly, if you have BA is equal to 0, it will imply that BA can be written as 0 into A. And this will imply that by right cancellation law, because we assume that the two cancellation law holds in R, so it implies that B is equal to 0. So in both the cases, when the two cancellation law holds in R, and whenever the product AB is equal to 0 with A different from 0, then we always have that, or we can always conclude that B is equal to 0. So this implies that R is a ring without 0 divisor. So this proves the theorem. In a ring R, the two cancellation law holds if and only if R is a ring without 0 divisors. Now next, let me come to this one. Integral domain. Definition of integral domain. A commutative ring with multiplicative identity 1 in which there do not exist any divisors of 0 is called an integral domain. That means, first of all, a ring should be a commutative ring. Commutative ring means that under multiplication, A into B is same as B into A. It has a multiplicative identity 1 for which A into 1 is always equal to A, which is same as 1 into A. And the second condition it must satisfy is this one, that there must exist no divisors of 0. That means whenever you have the product AB is equal to 0, then at least this will imply that at least one of the element must be equal to 0. Either A is equal to 0 or B must be equal to 0. So a commutative ring with multiplicative identity 1 in which that ring has no divisor of 0 will be called as an integral domain. The simple examples of this one is ring of integers under addition and multiplication. We know that the product of two integers can never, non-zero integers can never be 0. If the product is equal to 0, then at least one of the integer will be equal to 0. For example, 2 into 3 will never be equal to 0, or minus 1 into 2 is never equal to 0. Minus 2 into minus 5 also can be 0. The product will be equal to 0 only when one of the number is equal to 0 itself. But now if you take the ring of matrices M2 over set under addition and multiplication, this is not an integral domain. It has a multiplicative identity. It is not commutative in this case. Okay, I'll just cancel this one because we need a ring to be commutative. So here if you take the example of this ring, set 4, which contains 0 bar, 1 bar, 2 bar, 3 bar. Now we know that this is a ring under addition modulo 4 and multiplication modulo 4. So what we see is that 2 bar is not a 0 element. Take A to be 2 bar and B is equal to 2 bar. Then what is the product of 2 bar under multiplication modulo 4? 2 bar. 2 into 2 will become 4. If it is 4, then you divide it by 4. What is remainder obtained? It will be 0 bar. So you see that none of this A bar, none of the element A and B is equal to 0 bar, but their product become 0 bar. So this is a commutative ring which has multiplicative identity 1, but it has a 0 divisor. Therefore, set 4 is not an integral domain. So this is a simple examples of a ring which is a commutative ring with multiplicative identity 1 in which it has a 0 divisor. That means it is not an integral domain. Now in general we can show that set P under addition and multiplication modulo P is an integral domain. That means if P is a prime, that means if P is not a prime composite number, for example, let's set 4, set 6 and all this, there in this case you'll see that it will be not an integral domain. But if I take P is equal to 2, P is equal to 3, P is equal to 5, P is equal to 7 and so on, which is a prime number, then in that case it will be an integral domain. So now these are the elements of set P. Now here suppose you take let A and let A bar, B bar belong to set P. Then suppose A bar into B bar and a multiplication modulo P is equal to 0 bar. With assumption that A bar is not equal to 0 bar. So what I need to show is that B bar should be equal to 0 bar in order to conclude that set P is an integral domain. Now A bar into B bar under multiplication modulo P is equal to 0 bar implies that 0 is the remainder by definition of this one. Addition and multiplication modulo P. 0 is the remainder obtained when the product AB is divided by P. Now, if when P divides AB gives you the remainder 0, then in that case implies that AB is divisible by P. Now, if AB is divisible by P means that P divides AB. And by the property of prime number that you have done in the number theory, whenever a prime number divides the products of two numbers A and B, it implies that either P divides A or P divides B. Now here, if P divides A, it implies that A is a multiple of P. A is a multiple of P, which means that A bar A will be equal to 0 bar in set P, because it will give you the remainder 0 only when A is divided by P. So this is not possible as we assume that since A is not equal to 0 in set P, okay. So if A is not equal to 0 by the assumption, so it means that P should divide the second element, that is B. So if P divides B, it implies that the remainder or B is divisible by P. It means that remainder obtained here when P divides B will be 0 bar. So 0. So this implies that B bar should be equal to 0 bar in set P. Whenever the product A, B and the multiplication modulo P is equal to 0, with this one not equal to 0, but B must be equal to 0. So therefore, by definition of integral domain, since it is already a commutative ring, and also it has multiplicative identity 1 bar in this case. This is that multiplicative identity 1 bar. So therefore, this satisfies all the conditions of an integral domain. So it means that set P under addition modulo P, multiplication modulo P is an integral domain. IT here means integral domain. Now, if you take let me take another example, set 6, where 6 is not a prime number, which is 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Now, here what is, if you take A is equal to 2 bar, B is equal to 3 bar, then what is A into 3 bar or A into B under multiplication modulo 6? It is equal to 2 bar into 3 bar under multiplication modulo 6. Now, 2 into 3 gives you 6. Since it is equal to 6, so you divide it by 6. So when you divide it by 6, the remainder obtained now will be 0 bar. So this is 0 bar. Now you see that neither A is equal to, this is not equal to 0 bar, nor B is equal to 0 bar, because 3 bar is different from 0 bar, 2 bar is different from 0 bar. But their product under multiplication modulo 6 become 0 bar. So this means that set 6 and addition modulo 6, multiplication modulo 6, this one is not an integral domain. So set M in general will be an integral domain if and only if that M is a prime number, or set P will be an integral domain where P is a prime number. If it is not a prime number or if it is not a prime number but a composite number, you can see from this example it cannot be an integral domain.